All right. Hello, everyone. Thank you for coming to our session. Hope you're all having an amazing reInvent so far. I know today is last day, so really appreciate all of you for making it out here. Lucky for all of you, we have saved the best session for last. As a way of introduction, my name is Matthew Liam. I'm part of the data processing engineering team, so that includes EMR, Athena, MWA, Data Zone, as well as SageMaker. And I lead the solutions engineering team. I'm joined here by Aaron Fang, who is a principal engineer at Roblox. And today we're going to be covering cost-effective data processing on Amazon EMR. Primarily going to focus on cost, but also talk a little bit about scalability as well as ease of use and how they all kind of tie in together. So this is the agenda for today's session. I'm going to give a brief overview of our data processing and analytics services and talk a little bit about EMR. And then we'll go into a bit more detail on the specific innovations and product capabilities as it relates to scale, ease of use, and price performance. And then we'll look at some of the innovations in practice, how customers are using it, as well as some of the considerations and things like that. And then I'll pass it off to Aaron, who will cover Roblox's journey to cost-effective data processing at Roblox. So before we dive deeper, let me start with a quick overview of our data processing and analytics services. So our data processing and analytics services provides customers with comprehensive access to data using open source software, query engines, and tools to build with, including notebooks, visual ETL, as well as query editors. We support a number of popular frameworks like Apache Spark, Ray, and Python so that you can transform or prepare your data at any scale. In addition, if you need more real-time access to data, we provide a number of streaming frameworks like Apache Flink and Spark Streaming. And if you're just looking to access or do query analytics, you have a number of SQL engines like Trino that you're able to use. You're able to orchestrate all these different tools and software without having to manage any infrastructure with managed workflow for Apache Airflow. And on top of all of this, you have integration with Amazon Q Developer to assist with everything from data preparation, data integration, troubleshooting and debugging, as well as code generation. A big part of our data processing and analytics services is Amazon EMR. Amazon EMR provides performance-optimized runtime for Apache Spark and Trino, which allows you to get the best price performance for all your big data and analytics. We also provide a lot of flexibility in terms of deployment options. You can run EMR and EC2, EMR and EKS, as well as serverless. We have best-in-class security with recent support for native fine-grained access control on Spark, as well as recent improvements with CV handling, as well as TLS endpoint support. And lastly, we try to stay as current as possible. Within 30 days of an open source release, we try to make that available on EMR. So a lot of customers have had success with EMR. To highlight a few, the Unified Intelligence Platform at Salesforce manages a petabyte scale data lake and really wanted to focus on cost savings and efficiency. By leveraging EMR's ability to use hundreds of different types of instances, there are spot integration as well as managed scaling. They were able to process twice the amount of data and also save $1 million a month in costs. Another really great example is at Autodesk. Autodesk uses insights and analytics to provide better solutions and features for their customers. They came to us because they had reliability issues with their existing platform. And because data is a core component of their business, they needed a platform that could support their reliability needs and at the same time scale to their expected data growth trajectory. So by migrating to Amazon EMR, they were able to save 30% in costs while also increasing their security and reliability postures. Autodesk was able to achieve 99.8% availability and have not had a significant outage or downtime since the migration. So a lot of really great customer success stories. Let's take a deeper look at these specific innovations and capabilities that have enable these customers to achieve these results. So there are three key pillars that are critical foundations to any data processing platform. It has to be scalable, has to be purpose-built for performance and cost, and it has to be easy to use. We're going to spend some time in each of these different areas and see how Amazon EMR is innovating as it relates to cost-effective data processing. So starting with scalability, when we talk with customers, there's generally three buckets of problems. One is that provisioning is difficult, like getting capacity, figuring out which AZs to provision your clusters in, making sure those AZs have IPs. After the cluster is actually up and running, operating that cluster and making sure it stays healthy. So doing things like deployments on a running cluster that doesn't impact what's already running there. And then on top of that, you need to have monitoring and debugging, which is a pain point that we hear a lot from customers, making sure that when there are issues, you're notified right away and you have the right tools and logging observability to be able to root cause quickly. And so over the last few years, EMR has really focused on making these three areas easier for customers by providing flexibility and making decisions on your behalf. So starting with provisioning, EMR provides flexibility by being able to specify up to 30 different instances during cluster provisioning and a number of allocation strategies. So that means when EMR provisions, it'll look across all the different instances you've provided and choose the instance that provides the best one from a capacity perspective as well as costs. A large focus has also been around supporting really large clusters. So you can now run clusters with over 4,000 nodes and choose between 500 different instances for those nodes. And then in addition to that, we also have focused a lot on visibility and better debugging and monitoring. So during cluster provisioning, we provide real-time provisioning insights such as insufficient capacity errors, timeouts if your provisioning or scale-up is taking too long, and giving you actionable insights into like this AZ doesn't have enough IPs, so you should provision in a different one instead. So let's look at one of these features in more detail. AZ and instance selection is a large challenge that we hear from customers, especially when you're doing this across hundreds of different clusters, or even if you have a single cluster, doing it across hundreds or thousands of nodes. You have to make sure that you have enough IPs, and if you don't do it right, you end up running into insufficient capacity areas or failures in provisioning, and this leads to delays in your workload or pipeline. And so when we talked with customers, they told us that they kind of just want to provide their inputs, what instance types they want to use, their purchase options, and have the platform do the rest. Our existing availability zone and instance selection handled a lot of these different decisions for customers, but there were definitely still gaps. For example, when we would select the AZ, we would only do that based off a subset of the cluster and not look at the total cluster capacity. We also had limited choices in terms of allocation strategy, so one for spot and one for on-demand node. And lastly, we had a pretty rudimentary retry strategy where we would retry up to a certain time and then just kind of fail after that. So one of the improvements we made this year was prioritized allocation strategy, which allows customers to set a priority level for different instance types. And on a best effort basis, EMR will try those instances first before falling back to lower priority ones. This is really great for use cases where maybe you want to try a latest generation instance first, or maybe there's instance types where you know your workload will perform better. So you want to try those ones, and then if you still want to get capacity, you try older generations or like something else in your pool. So with prioritized allocation strategy and a number of other improvements that we made, this is kind of our new flow. We now pick AZs and capacity we look across the whole total cluster now. We still fall back to the essential nodes, so just primary and core, because we've heard from customers that sometimes they just want to get their cluster started and then scale up afterwards. We support a number of other allocation strategies. So in addition to prioritized allocation, things like diversified, lowest price, and capacity optimized. We also have a feature during provisioning that will switch to on-demand, so you can try provisioning your cluster with Spot, and if there's no capacity, we'll go to on-demand instead. And then lastly, we have a bit more flexibility in terms of the retry strategy. So there's a user-defined input and allows you to keep retrying up to that amount or fail fast quickly. So now that you have provisioned your cluster and it's up and running, you now have to operate it and keep it healthy. And that's another challenge that we hear from customers. You have to handle different scenarios like hardware failure or replacing unhealthy instances. Another challenge that we often hear is making changes or bringing up a new cluster and without having to impact what's already running on your existing cluster. EMR simplifies many of these operations for you. One in particular that I wanted to call out is our automatic replacement for unhealthy nodes. So with running large clusters at scale, unhealthy nodes is a common problem, and they can occur for a number of reasons. For example, EC2 has an impaired node, or maybe the application you have running on your cluster is causing disk space issues, or maybe there's network issues on your instance and your node has now become unresponsive. So with Amazon EMR, we're constantly monitoring all the nodes so that your jobs can constantly run successfully on them. The worst case scenario is if you have an instance that's running and it's not actually doing any work, but you're still paying for it. If EMR detects an unhealthy node, it'll gracefully decommission that node and then provision a new instance in its place to get back to your target capacity. So this flow captures many of the different decisions we're making for you on your behalf. For example, we only decommission a few nodes at a time to make sure that we're not impacting what's already running on the cluster. Another thing we do is because we're transferring data from the unhealthy nodes to the remaining healthy nodes, we do checks and balances to make sure the remaining nodes have enough storage and we're not causing other issues if we were to move all the data to the healthy nodes. So since its release, we've replaced over 1.1 million nodes per month across all our regions. What this means for you is less impact to your workloads and lower costs because you're not having to rerun these tasks or jobs. Okay, so now that your cluster is staying up and running healthy, the next thing we want to focus on is monitoring and debugging and getting enough insights on what's happening on your cluster. So with monitoring and debugging, our innovations here and focus over the last year has been providing real-time alerts and events as quick as possible so you know what's happening on your cluster. Secondly, it is making it easy for you to integrate with your existing observability, logging, and monitoring solutions. And three, providing managed web interfaces and pre-built dashboards so you have easy access to know what's happening on your cluster as well as all the important information. So one specific example of this is how we emit CloudWatch events and metrics. So in 2024, to improve visibility, EMR achieved 99% coverage of customer actionable insights. This includes everything from insufficient capacity areas, different resize timeouts, different limits that you may be hitting like vCPU limits or instance limits and spot interruptions. How we did this was we built a central control plane layer where internal teams were able to publish their own metrics as they built different features, and that would automatically get surfaced to customers' EMR consoles as well as EventBridge. So for those customers that wanted to build automation through something like event-driven architecture, they could use an event like this where they would kind of ingest it and see, for example, this one is insufficient capacity, and they could take action on it, whether it's provisioning a new cluster in parallel or maybe at least notifying their downstream teams that we have a delay and your data may take longer than normal. For those that still want an interactive experience, we still have the AWS console where the same events are shown. All right, so running your data processing at scale is really important, but you also want to do it in a cost and performant way. When we talk to customers about price performance, the main challenges we hear is that tuning is difficult, choosing your infrastructure is a pain point, as well as managing storage. And so across all of these areas, EMR has focused on automatically determining the best set of configurations and code so that you can achieve the best price performance. One of our key innovations that enable this is our optimized runtime for Apache Spark and Trino. EMR's Spark, with our latest release, is 3.9 times faster than open source compared to TPCDS benchmark on 3 terabyte of data. EMR Trino is 2.7 times faster than open source on TPCDS benchmark as well, and both are 100% API compatible, meaning you can take your existing Spark workloads and run them on EMR without having to make any code changes or configuration changes. In addition, all of these optimizations are enabled by default and are adaptive, meaning they adjust based off the workload that's running, the data that's being scanned, or the hardware or infrastructure that it's being run on. To give you an example of this, let's look at tuning. So as many of you are probably aware, tuning is a pretty challenging process. You have to pick a set of configurations for a workload, and those configurations likely don't apply to any of your other workloads. And because data is constantly changing and evolving, the configurations you choose today may not be the best configurations for your workload when they run in 1 month. So to help customers with this, EMR Spark has made optimizations to handle these type of configuration choices for you to get the best price performance. An example of this is with our shuffle partitions. EMR will automatically try to determine what is the best shuffle partition, and as a result, parallelism, based off the workload and based off the infrastructure that workload is currently running on. Another really good example of this is with adaptive join selection. So when your Spark application runs, there's a number of different joins that can occur, either like sort, merge join, shuffle hash joins, broadcast joins. And ideally, you're supposed to provide hints into your data, like the tables that are being joined, the size of these. But EMR will automatically take those inputs and look at like the data that's being scanned, the tables and the join keys, and automatically choose the most efficient join type so that your workload has the best price performance. So auto-tuning of configs is not the only area. On the infrastructure side, a common challenge that we hear is making sure that the hardware that you choose is fully utilizing the instance. And this is especially challenging when you have a large cluster of mixed instance families and sizes. So to help customers with this, we have optimized default executors that change depending on what instance the workload is running on. We also have a feature that will dynamically change the size of the executor so that you can get maximum utilization and you don't have to worry about like sizing all different executors for every single instance type that you use. Lastly, there's a storage interaction. So with decoupled compute and storing all your data in S3, that interaction between S3 and your like engine and application is really important. You have to think about like S3 throttling, small files, sometimes the network between the application and storage becomes a bottleneck with your application. And so based off this, the areas that we've invested in is around reducing our interaction with S3. So for example, when we can write directly to S3 rather than having to do a multi-operation rename, we'll do that. In addition, we try to reduce the amount of data we need to scan, so pushing down filters further down the Spark application stage. And for the data that we actually do need to bring in, trying to parallelize that as much as possible. So one example of this is with data prefetch. With data prefetch, before the Spark task needs to run, we'll try to asynchronously prefetch all of that data with excess network bandwidth so that when the stage comes, the data is already there and we can start rather than having to pull in all the data at that time. So these are just a few examples that we're investing in. Our focus here continues to be around trying to do these optimizations out of the box and making these configuration choices for you. So we've talked about scale, we've talked about price performance, but it also has to be easy to use. Our innovations here have focused on trying to handle the undifferentiated heavy lifting that's required when it comes to data processing. So for example, making sure that our native integration with your orchestration system or your observability system is seamless. In Matt's keynote, he also talked about a unified studio for all data processing, Gen AI, AI/ML. Prior to that, you'd kind of have to stitch all these different pieces together, but now you have one place for all your data needs. Another thing I want to call out is just our flexibility across different deployment options. So you can run your Spark applications on EMR and EC2, EMR and EKS, as well as serverless. The one I wanted to focus on today is our improvements with managed scaling. So EMR supported managed scaling, which provided a pretty hands-off approach. You would define your maximum, your minimum, the number of core nodes, spot nodes, and EMR would handle the rest. Customers really appreciated the simplicity, and we saw a lot of great results. We heard from customers that would save up to 60% by just enabling the feature for some of their workloads. Our current optimization was very optimized for SLA-sensitive workloads. And by that, I mean during scale-up, we would optimize for performance and try to give you as much capacity as quick as possible because we didn't want scaling up to be a bottleneck for your workload. And then on the scale-down side, we'd be a bit more conservative and wait until the job is fully complete before scaling down, making the decision to scale down. And then once we knew it was safe, we would scale down pretty aggressively. This worked for many different workloads, but in some cases, it would lead to underutilization. So for example, spiky workloads where you have a huge increase in tasks and they're short running. By the time we scale up, maybe a portion or all of those tasks are already finished and we don't actually need the instance that we had provisioned. Or similarly, on the scale down side, we heard from customers that knew they had workloads that were in the pipeline and they wanted to not scale down so aggressively and keep those instances running as sort of a warm pool. So to support these use cases, we released advanced scaling. With advanced scaling, you now have increased flexibility to define your intention, whether it be optimized for cost or optimized for performance, and Amazon EMR will automatically adjust kind of the algorithm based off the specific intent that you've specified. So for example, if I wanted something that's optimized for costs, you may see something like this, where the scale-up behavior is a bit more conservative. We'll scale up to a certain percentage and kind of assess that do we need to continue scaling up or have the nodes that we've already provisioned is enough and we don't need to scale up further. On the scale down side, it would be pretty aggressive because here we're trying to optimize for utilization and costs. So once we know we don't need the instances, we'll shut down pretty quickly. And if we wanted to be optimized for performance, the scale up would be something similar to what we have today, where we try to get you as much capacity as quick as possible. And then on the scale down side, it would be a bit more gradual because again, we don't want to have scale down impact your workload and have you to rerun any like tasks or applications. Advanced scaling is just one example, but the general theme here is to try to do as much as possible for you and to reduce the operational overhead with managing data processing platforms. Okay, so we've covered innovations in scale, price performance, as well as ease of use. We'll look at some of these innovations in practice and considerations and how customers are using it. So the first thing I wanted to discuss today is around how to choose the best EMR deployment model from a cost perspective. In ease of use, we talked about how you can use EMR and EC2, EMR EKS, as well as EMR serverless, and the one from the best cost depends on a number of factors. To understand this, let's first look at our pricing kind of structure. So across all our EMR deployment models, we have the EC2 costs and the service costs. There's other costs like storage costs and network costs, but for the purpose of this, we'll just focus on these two. EMR and EC2 and EMR and EKS are our cluster-based deployment models, and they have an EC2 cost because these EC2 instances run in your own account. So they follow, the standard hourly pricing model, depending on the size of your instance. If you have something like spot or savings plans, these get applied here. EMR serverless runs completely in our own account, so there's no EC2 costs here. For the EMR service costs, with EMR and EC2, it's a very similar pricing structure as EC2, where it's an hourly pricing dependent on the size of the instance, usually around 25% of the EC2 costs. With EMR and EKS and EMR serverless, it is a consumption-based model, so it depends on the aggregate vCPU and memory that your application is using. To better understand this, let's look at a cost example. So suppose you had a Spark application and it uses 25 R5 4x large instances to run. And to complete the application, it uses 80% of that cluster's utilization, and it runs for 3 hours. So on the EMR and EC2 side, the calculation is pretty straightforward. You take the number of instances, and I have 26 there because I accounted one for the primary node. So you take the number of instances, you multiply it by how long it runs for, and the hourly rate for EC2 and EMR. If you add all of those together, you get around $98. On the serverless side, again, there's no EC2 costs because everything runs in our own account. For the service costs, you have to look at the total usage that your application is using from a vCPU perspective and memory perspective. So in this case, we said 80% utilization for 3 hours. So if you take that total cluster capacity, multiply it by 80%, and then 3 hours, you get around 960 vCPU and 7,600 gigabytes of memory. If you plug that into our hourly rate for vCPU and memory, you get around $95. So the key takeaway here is that utilization is a key factor when comparing hourly pricing models versus like consumption ones like EKS and serverless. For example, if this workload was actually 50% and not 80%, your EC2 costs would actually still be the same because, again, it's not dependent on the usage. You're still paying that hourly rate, but your serverless costs would drop down pretty significantly to around like $70 or $60. And so if you were to kind of expand on that and plot utilization as a function of change of costs between EMR and EC2 versus serverless, you'd get something like this. And we have found that 70% utilization is kind of that break even using on-demand public pricing, where if your EMR and EC2 cluster is greater than 70% utilization, then EMR and EC2 is generally a more cost-effective option. Whereas if your utilization is lower than 70%, then the consumption-based ones like EKS and serverless can be lower in cost. And so because utilization is such an important factor, it's good to understand like what goes into the calculation of utilization because it's more than just the workload itself. So for example, on the infrastructure side, cluster scale-up time is an important consideration. With EMR and EC2, we provide the flexibility to bootstrap your cluster in a way that meets security needs or pre-packages application libraries for your job to run. But one of the trade-offs with that is that adds to the cluster startup time. And because that is time you are paying on the EC2 side, it needs to be factored into your overall utilization calculation. On the workload side, we've seen that certain workload types just generally have better utilization. We have some customers who run streaming applications and they know that they need like 10 or 15 executors always running all the time, and they will size their instances to perfectly fit those executors. So in those cases, your utilization is going to be really high, and EMR and EC2 is likely the best cost option. The last thing I just want to call out is when you're comparing EMR deployment options, cost is just one factor. There's other things that you should take into consideration as well, including operational overhead, managing cluster versus serverless. With EKS, do you have the team to manage an EKS cluster and expertise in that? But for this example, we're just looking at costs. Okay, so the next innovation and practice that I wanted to cover is balancing purchase options and instance flexibility, because I think this is one of the most critical things when running cost-effective data processing. So the first thing to start is choosing between different purchase options. It's fairly straightforward. If you have like critical workloads or SLA sensitive workloads, you want to keep those on demand for like dev testing or jobs that you don't mind are able to fail, you can run on Spot. An interesting call out here is that even though Spot can sometimes give you 90% of on-demand, in a lot of cases we've seen Spot still costs more than on-demand because of the amount of like retries or because of the Spot interruptions. It just causes your job to keep running and ends up being higher in costs than if you were to just run on on-demand. So one strategy that we see with customers is kind of mixing on-demand and Spot together on the same cluster. So you'll have a portion of your cluster that's on-demand for predictability, to achieve that SLA in case you don't have Spot. And then they'll add on Spot to get additional compute at a lower average cost. So to give you an example of this, say you had a cluster in the first bar here where it's just on-demand nodes and it runs for 10 hours and the cost to run that cluster is $100 represented by the yellow line there. If you were to convert that cluster completely to Spot, it would still run for 10 hours, assuming the Spot cost here is 50% of on-demand. So your cost goes down from $100 to $50. Now, if you were to combine the two, kind of take the best of both worlds and have 10 nodes of on-demand, 10 nodes of Spot, you now have double the compute. So assuming linear performance, your runtime would go down from 10 hours to 5 hours, but you've now also reduced your costs because now you have a blended rate between your on-demand hourly rate and your Spot on-demand rate. So you'd see an improvement in cost as well from $100 to $75. So incorporating Spot is really important. And one of the most critical factors in being able to use cost effectively is being flexible across different AZs and instances. EMR and EC2 and EMR and EKS provide you the ability to specify up to 30 different instances. And what EMR will do is look across those different instances and choose which instances is least likely to be interrupted by Spot. That doesn't mean you want to just randomly choose these different 30 instances. There is a kind of order and way in which you want to diversify and increase your instance pool. So as an example, say for your application, you've determined that R family 2x large is the best instance type and size for your workload. The first thing you want to do is diversify across different availability zones. So take your, say, R8 2x large and run it across all your different AZs. After you've done that, you want to diversify across different sizes. So 4x, 8x, 16x, even though they're larger in size, they're not going to cost more. Your workload will just be able to run more in parallel. After you've diversified there, you want to add different generations and variants like 7th generation, 6th generation, include AMD and Intel. The reason you do instance family last is because different instance families have different vCPU to memory ratios, and that is what can lead to underutilization. So key takeaway here is that more diversification equals lower costs. The other consideration you want to think about in addition to infrastructure and workload is the actual workload itself and how tolerant you are to failures. So to understand this, we took an EMR cluster and every 5 minutes we would simulate Spot interruptions where we would take away 20% of the nodes. And on this cluster, we would run hundreds of different Spark applications where each Spark application's task all had the same task runtime. Because we're trying to understand how does task runtime get impacted by Spot interruptions. And so what we found was that for the Spark applications whose task runtime was under 120 seconds, there was almost no impact to their job runtimes. They pretty much perform the same as if they were running on like on demand, for example. Once the Spark application's tasks exceeded 120 seconds, that's when we started to see a lot more job failures and as a result, longer runtimes. And the reason this occurs is because when a spot interruption occurs, EC2 gives you like this 2-minute window or grace period to finish running everything before it takes it away. So if your Spark tasks are under 120 seconds, you'll have enough time to finish before EC2 takes it away. In addition to this, EMR has a feature where once we know a node will be taken away due to spot, we stop assigning tasks to it. So that also prevents like failures and having to rerun. So the key takeaway here is shorter task runtimes equals less impact due to spot. I know that in some cases you can't control the task runtime due to the data or application. So in those cases, it may be better to run them on demand. Okay, so that wraps up my part. Thank you again for taking the time to listen to our innovations in scale, data processing, and ease of use. I'm now going to pass it off to Aaron, who will cover Roblox's journey to effective data processing on EMR. Aaron.
All right, thanks, Matt. Matt, he went over putting in depth on the product side. Today, we're going to talk about our journey and also more on the operational side, how we use EMR. Before we get started, I'm sure a lot of you have heard about the company before. Just in case you haven't heard of Roblox before, that we're a 3D experience platform that we provide the tooling on the client side. We also host these experiences on the server side too. So we have a complete ecosystem for the 3D experiences. And today we have 6 million active experiences. And the way to kind of think about us is that in some ways we're closer to maybe like YouTube in terms of all contents are user generated than you're a typical gaming company, since we don't actually publish any experiences. And the one thing I notice a lot of times people will say gaming company, that I always use the phrase of 3D experiences just because we provide a wide variety of 3D experiences. Gaming is just one aspect of it. For example, we're communication, shopping, entertainment, learning, of course, playing games. And as of Q3 2024, we have had 88.9 million daily active users, and that all those daily active users, that is around 20.7 billion engagement hours, and we have 2.9 million devs on our platform. And just a quick agenda before we kind of dive into our journey. At first, going to talk a little bit about the scale of our data platform. Then we'll talk a little bit about where we started in EMR and where we are today. And also just a quick architectural, very high level architectural overview about our batch platform. And since I work on the data infra side, I think a lot about DevOps and also things on the infrastructure side of things. And of course, we also wanted to understand cost in the end, and hope I can help everybody save some money here. All right, unfortunately, I can't give you the actual numbers, but here you should be able to kind of gauge the scale where we're at. Currently, we have hundreds of petabytes on S3. Our data lake is in S3, so we store everything in S3. And we increase our S3 storage by tens of petabytes every single month. And our internal services within our data centers, we generate trillions of events every single day. And we have tens of thousands of active pipelines that are running. And so in some ways that our data platform is not just used by the 100 or 1,000 people in our company, is trickle down to the millions of devs that's using our platform. So this is just a very high level what our batch processing look like. Like I said before, all the data that we send from our data center, we ingest it into S3. We obviously have more than 2 data centers. It just kind of, this fits better on the screen here. And on the right-hand side, you can kind of see this is a typical open source platform that all our pipeline is written using Apache Airflow. Of course, we use EMR. Then we write all the data back to S3. And for dashboarding and ad hoc querying, we use Apache Superset. And for shorter running queries, anything less than 1 minute, we would typically run Trino. All right, that's kind of talk a little bit about our journey. We actually started using EMR in 2016. I joined the company in 2020. So I was able to find a few people that were here in 2016, kind of asked them about their EMR setup and experience. So my understanding is that back in 2016, that we had 2 to 4 shared cluster set up, maybe 100 nodes, maybe a little bit more, maybe a little bit less. And so during that time, basically somebody will spin up the EMR cluster when they need to process, and they will shut the cluster down. So if we fast forward to 2020 when I joined, still the same 2 to 4 cluster share setup, but now we're running thousands of nodes. The problem that I was tasked to think about is that we have thousands of nodes, but we still cannot run all the pipelines that we have today. So how do we scale out EMR so all the pipelines can run? One thing to know is once we start an EMR cluster, we never shut them down now. And so basically all the pipelines are running 24/7. It is the heaviest at UTC 0, but in general, the pipelines are we're always running something. And so let's think about how we can scale out. So the way we scale out is pretty much what you expect. It's pretty simple in the sense that instead going share cluster setup, so we decided to say, hey, why don't we just kind of break this down by teams? So here, the problem here is that some teams may have different workloads. We can configure EMR to run mixed workloads, but sometimes the workloads are so different, it's actually pretty hard to do. So then what we're starting to do is let's scale out by workload types. So imagine you may have high-tier pipelines that you want to run, and you may have a dashboard or some dashboards that you want to run quickly. You don't want those two blocking each other. And maybe lastly, you want to do some backfill, right? And you obviously don't want your backfill pipelines to interrupt your high-tier pipelines. So it's pretty straightforward. The issue here is that instead going from 2 to 4 clusters, we're going from that to say 30, 40, 50, 70, 80 EMR clusters. So even though EMR is relatively easy to provision by hand when you have a small amount of clusters, but when you have this many, it gets hard, right? And also, of course, the costs start to kind of go up a little bit more. But the first problem we're trying to solve is how do we get all the pipeline to run within their SLA? So this is kind of where I think a lot about DevOps, and that in order to provision these EMR clusters, what we really want is to come up with the tooling to ensure there's no configuration drift across all the EMR clusters that we have. So we roll an internal tool to do this, and the great thing with internal tooling is we have our own internal configuration, so which leads to allow our internal users to self-provision their EMR cluster in some cases. And the last thing I don't really see a lot of people do with EMR is that the blue-green deployment. And also, since we have an automated solution to do this, we can easily extend it to do the blue-green deployment. The way we think about deploying EMR is very similar how I think about, or how we think about deploying, any kind of microservices. So this is kind of a simplified diagram how we do our blue-green deployment. So one thing to note is that at any given time, there can be 2 copies of one workload type EMR cluster. So for example, let's say we start out with the green one here. And so everything in that box, we consider EMR, even though there's more things than EMR, because there are some cases where maybe a user, they wanted to read some buckets they currently don't have access to, or they may want to write to some buckets. So we'll also provision that. In some cases, we'll do EOB in front of the EMR because some of our EMR cluster are running in the private VPC subnet that's non-routable IPs. And on top of that, we also use Route 53 because we're doing blue-green here. We want to easily be able to switch from one cluster to the next. And the other thing that we also do is on the CloudWatch side, we do our dashboarding, metrics, logging, alerting, all inside CloudWatch. So we start out with the green cluster. Then say maybe somebody wants to make a configuration change, we never make configuration change in place. Because when you do that, you may have to restart things, so existing pipeline may fail. And also, what if you messed up the configuration, right? Then you're going to cause more downtime. So the idea is we never want to cause any downtime. So we make the new blue cluster out of band, basically. And what we do is from Airflow, we redirect small amount of traffic to it to make sure the cluster setup is right. Once everything's right, we redirect all the 100% traffic into the new cluster. Then because our pipeline, some of them can run for many, many hours, this also allows the green cluster to drain all the pipelines. So once the pipelines have drained, then we'll delete the green cluster. Now we're back to 1, okay? And let's say if anything were to fail, we still have the old one. We can still go back to the old green cluster. All right, so now we can kind of, you can kind of see we can start having the tooling to scale out EMR. The problem right now is now we need to understand the costs, right? So we think about costs as several different levels. For example, at the highest level, we think about at the org level. That's pretty simple in the org level, in the sense like the data org, how much data org is costing the whole company. So that's pretty simple. You just add up all the Amazon accounts, then that's your total. But the next tier down is the cluster level. We tag all our EMR cluster with the team name. So it's easy for a team to understand these clusters that we own, and these are what's our costs, right? And the last two things is a little bit more interesting, that you don't get those two out of the box that we do internally, that we wanted to be able to do job estimation. A lot of times you have a team may have a lot of pipelines running on the cluster, but they don't really understand how much these jobs are costing them. So what we do is we do a high-level estimation. I will talk about that a little bit later. And the last thing is that we provide a portal, so any user can just log in to understand how much how efficient they are and how much their pipeline is costing the company. Instead of going to a bunch of different places, we aggregated that data into a single place. So one thing to know is this is a very high-level explanation of job estimation. This is it's an estimation because it's not the exact amount. There is several factors here that we actually don't know the exact amount, or it's from our experience, it's not really worth to figure out the exact amount because the estimation comes actually really close. So there are two pieces puzzle that you need here. One, we need to know most of our jobs are memory bound. You need to know how much memory is consuming and how long the job has been running, which you can get from the Young Resource Manager. The one thing that we look at a lot is the value is called memory seconds. It's a kind of funky value that returns basically is the total consumed memory in megabytes times the amount of seconds that the job has been running. And couple that with the instance cost, and you can estimate that. We run many different instance types, so we just take an average, the most common launch instance here. So this is why this is not the exact science here. So, but the instance type is basically a constant. So at least when the users keep running the pipeline, they can know compared to with the old cost too. So this is the team automated report that we're working on internally. So there's two things that are important here, that we want the teams to be as efficient as possible. So at the very high level, we just provide an efficiency score. So you don't have to kind of dig down into the data. It's like, hey, am I efficient or am I not? And the way we figure out the efficiency score is that there's two things that we look at: the storage cost and the compute cost. Are you wasting storage or are you wasting compute? So the way we figure out the storage cost is that we parse S3 logs. So we know if your pipeline generated some data set is never being read, we consider that that's a waste. And through the data set, we know what pipelines are being run, right? So that means it's the compute waste. And we can keep going up. Since we schedule all the job in Airflow, in some cases we have seen that jobs will fail for like 4 or 5 times before it succeeds, right? So we count those 4 or 5 times as also waste. So the idea is when you come in here, you understand how much money you're spending and how efficient you are. And if you're not, you can kind of dig in to figure out why your pipeline is not efficient. All right, so now we can scale everything out. So let's talk a little bit about cost savings. The first few things are pretty obvious, and the last two things I think gets a little bit more interesting. So since our data lake is in S3, we have tons of data. It's worthwhile to turn on the S3 intelligent tiering. So essentially just a button that you click that S3 after 90 days will figure out what tier to put your data in. And so if there's some data that you want to keep, but maybe it's rarely accessed, it will put it in a cold storage for you. And the EBS volume type, we didn't really save a ton of money, but the more of that is anytime when Amazon comes with a new instance type of anything, it's always worthwhile to look at because the price is always cheaper and also more performant. So for us, go to GP2 to GP3. that we actually save some money, but what we really got out of it is a higher burst rate of GP3. And Matt talked a little bit about this spot versus on-demand, that our pipelines runs usually fairly long, so we try to use spot instances. In the end, it actually costs us more money, so what we try to do is just optimize more on the on-demand side of things. And before I was saying we start scaling out to lots of EMR clusters, it turns out some of the teams that they didn't really need different workload types just because their demand's not really that high. So in those cases, we consolidate down into a smaller subset of clusters. And if you know your minimum compute usage, it's also good to kind of talk to Amazon in terms of can get on a savings plan in terms of the minimum compute that you're going to be used every single month, and that can save you a good bit of money. The last two things I think is pretty interesting that we do it in-house is job auto-tuning. That since we have tens of thousands of pipelines, it's impossible to tune all these pipelines by hand. So what we want to do is to auto-tune, making sure that no resources are being wasted. And the last thing is that we started to use managed auto-scaling, like Matt talked about earlier, that managed auto-scaling can be really sensitive. So what we really want to do is making it work better for us because we know how often we are running these pipelines. And that, I think, that probably save us, those last two things roughly save us 30% to 35% of our overall EMR cost. So let's talk a little bit high level about job auto-tuning. So the way it works is that when you create a new pipeline, we will let it run 3 times. So each time it runs, when the Spark job runs, we actually collecting all the metrics and store in the database. When the 4th time comes online, we basically say, hey, is this configuration optimized? And there's a lot of different things that we look at. The 2 things that commonly we look at is the executed memory. Usually people have that number way too big because they're copy and paste from one job to another. And so what we do is we look back the 3 runs and we take the top 1% memory allocation for all the executors and we times that by 1.5. So basically the 0.5 is to give you a little bit of a headroom. And as you can see, the bottom graph, the memory usage drop. The magical part about this is that we are not doing anything. We just let the pipeline run. And another thing that's commonly we look at is the number of executors. The dynamic executor value is sometimes set too high. So what we will do is we'll look at all the executor across your runs and trying to figure out if they are less than 2 or 3 minutes. If they're less than 2 or 3 minutes, we consider that's too short. So we'll actually reduce your executor count. So the thing to know is that the auto-tuning is always running. So over time, the jobs will get better. And if anytime it fails, we'll revert back to the old configuration so we don't create much of a disruption. And this is kind of my favorite thing to talk about. I call it cluster auto-tuning. I think internally we have a few different names. The one thing that Matt was talking about earlier is that managed auto-scaling can be really aggressive. We pick managed auto-scaling because it can respond within 5 to 10 seconds. Normal auto-scaling, I think it checks only every 5 minutes. So we obviously want that, but we also don't want it to scale up and down really fast. So there are 3 lines up there. The blue line is basically the cluster maximum capacity. So generally when you do managed auto-scaling, you just tell it how much maximum capacity you want, and typically it will just scale up to that no matter what. And so the other 2 lines is the memory available and memory allocated. You want those 2 lines to be pretty close together. So on the left side, top left side, you can see there's a lot of scaling up and down. On the right side is when we turn on the cluster auto tuner, it basically made it better, doesn't scaling up and down as much, but this area, there's still a lot of wasted memory. So here, if you look on the bottom, this is a much more optimized cluster. So basically, we'll hold the cluster up as long as possible. Then we'll essentially change the managed configuration on the fly. So the way that we do this is we wanted to create some back pressure to the cluster. So the 2 values that we commonly look at, there's more metrics that we look at. The 2 that we look at a lot is application pending and containers pending. So we want that back pressure. Once the application pending and container pending gets to a certain value, we'll actually specify a new managed auto-scaling configuration. Then when the when there's not enough back pressure, we actually change the configuration to much, much lower. So this is why you see, the available capacity was super high, then now is super low here. So that in turn actually saved us a good bit of money. And I think Matt was kind of talking about the managed autoscaling, advanced autoscaling feature. I think a lot of it can do something similar to this. All right, so we're getting towards the end. These are the kind of the three things that I went over today. On the DevOps side of things, that you can actually save money if you have a repeated automated deployment tool, because for us, we can do the blue-green deployment that we don't create any downtimes. And the other part is that we have so many pipelines, there's no way that we can tune them by hand, right? So be able to auto-tune the jobs, and also on the cluster side of things, save us huge amount of money. And the last thing is that there may be certain things cannot be caught by some automation, that we want to provide visibility to our teams, in terms of how much they're spending and if they're doing things in a proper way or not. All right, and that's my part, and I'm going to pass it back to Matt.
Cool, thanks, Aaron. Okay, so quickly, just to close, summary of some of the key learnings and kind of takeaways from our talk. The first is always use the latest EMR release and version. We're constantly working on trying to improve the performance of our runtimes and engines, and those typically will go to the latest version of EMR. Use instance fleets to diversify across as many different instances. This will give you the best possible outcome from a capacity perspective as well as costs. Prioritize allocation strategy is a cool feature to use if you want to try using latest generation or instances that will work better. Advanced managed scaling is something you should look into if you want to have a balance between optimize for cost or performance or somewhere in between. When you are considering different EMR deployment options and you're making a decision based off cost, utilization is a key factor. And then the last two, when you're looking at using Spot, try mixing on-demand and Spot together on the same cluster. You kind of get the best of both worlds, where on-demand gives you the stability and Spot gives you that extra compute at a lower average cost. And then lastly, Spark applications with low task runtimes are generally more effective on Spot nodes, because when you have Spark applications with long-running tasks or the cost to rerun those tasks are expensive, then those workloads don't work well on Spot for most of the time. So with that, thank you again for the time and listening to our presentation, and I hope you have a good rest of reInvent. We'll be around if you have any questions around EMR or any of the specifics from this presentation. Thank you.